All right, so here in this lesson, we are going to look at the most direct application of one-to-one functions. Okay, so needless to say, this lesson here must be viewed after you have learned and viewed my lecture, particularly or specifically on one-to-one functions. Because this lecture we are doing here is once again built on top of our understanding of what it means by being a one-to-one function. So this is here again. It's a direct application of a one-to-one function. Okay, and so now what we're looking at now is we're gonna investigate and we're gonna learn about inverse functions. Okay, and so as another high recommendation, I highly recommend this video lesson here to be viewed after you have learned about the composition of more than one functions together. Okay, so or in short, I've had that lecture about the compositions of functions, and further, it's highly recommended that you have seen this. It's highly recommended that you are viewing this lesson after you have learned about all the transformations of a function. But this last recommendation is not as highly recommended as the earlier recommendations. But other than that, let's dive in. Okay. All right, so now let me bring up the following example. All right, so, and to maximize the space, allow me to erase this title of our discussion topic here. So now I'm going to just start out with a function right here. All right, we're going to have a function f of x given to be about 2x plus 3. Okay, one small little function. And so we have seen, and of course, needless to say, at this point viewing this lesson, anyone must be fluent with what it means by having a function and how to construct a table of values, and learn that and must have learned that we can represent a function through a table of values. And so I'm going to construct a table of values for this function. Okay, so let's look at, and just stay in the usual convention. The x here is the input, the variable x here is the input variable, okay? And then the output is going to be assigned to the y variable to keep it in that tradition right there. So the inputs here, and let me sketch down a few. So how about 0, 1, 2, 3, 6, and 8. All right, so I'm sketching down about 6 different values. So now the y value here comes out, of course, as the output of this function. So a function is a rule. So this rule, the rule of this function here, the rule that's represented by this function f, says for every input x, we're going to multiply the inputs by 2 and add 3. Okay, so in that way, according to the rule, then with inputs now currently x equals 0, then we're going to look at so 3. Okay. That's simple. That's the output because the input's 0 times 2 and plus 3. That's how we got 3. Okay, and then in this, when input x equals 1, we're looking at 5. When input x equals 2, we're looking at 7. And once again, you can always pause the video at any time to double check with my calculation here. When input x equals 3, according to this rule, we're going to come out with the outputs being 9. Okay, and then with this input x equals 6, we're going to come out with 15. Okay, we're going to come out with 15. And then with that input right here, right, we're going to come out with 19. All right, and so once again, you can always pause the video to double check my calculation. All right, and so now, that's just the table of values for this. And just a couple things to notice about this function f. And that's all I would like to point out for now. Okay, we have a function here. Yes, this function, if you've learned, if you know it or if you don't, that's okay. But we call this function the linear function. Okay, so a couple things now I would like to point out as what I have noticed about this function. And by the way, this function here, the table of values, I'm only listing out a few input values. I mean, this function is supposed to have a lot more input values than that. So this table did not represent the entire function like that. Okay, so it's a linear function. but this one here is not too important. It's just something. The reason I call it linear because sketching the graph right here, once we represent this function here graphically, it's going to produce a line. Okay, but all that details don't need to be brought into this particular discussion right now. Now this function, after what I've talked about in the beginning, the part of this video, this function here is a one-to-one function. All right, this function here is a one-to-one function, and I want you to focus on this understanding a little bit. So you feel free to pause your video and apply your understanding from my earlier lecture about a one-to-one function so that you can verify this function here is a one-to-one function. Okay, you can apply your understanding that you have learned from my earlier video lecture, and as I said, this lesson here is viewed, it must be watched after you have learned what a one-to-one function is. And in that lecture there, I have brought it in different ways, different methods, how you can check and verify if a function is one-to-one. So now I'm telling you here right now about this function. It's a 2x plus 3. This f of x equals 2x plus 3. It's a one-to-one function. Okay, it's a one-to-one function. And specifically the domain for this function. And you have learned how to find domain and range of a function prior to this point. So the domain of this function is the interval anywhere from -infinity to infinity. Okay, so now with the two information here, you can always double check to see if what I set up here is to clarify what I set up here. All right, within this domain, this function here is one-to-one. All right, so double check on that. Okay, so now assuming you have already double checked, okay, then let's move on to another function. So that's all. That's all for this function. That's all of the intention about that function, and I will make that connection later. Okay, so now on my other board here, allow me to introduce another function. Okay, so now how about let's say it's g of x here. I brought up f of x. We stopped talking about it. Now I'm looking at a different function here. G of x here is, how about all right, so how about x minus 3 over 2. X minus 3 over 2. Okay, or you can write this as you can also see this function as another linear function. It's a 1/2 x minus 3/2. It's just a different algebraic expression. If you would like to write it this way or you would like to write it this way, that's pretty much your choice there. But what I want you to see, it's a completely different function. Okay, nothing related to the earlier function at all. Okay, nothing related right now, nothing as of this moment, nothing related with the f of x that I brought up previously. Okay, and then again, let's look at a few values and list it down as a table of values here. Okay, let's just construct a table of values and list down a few inputs value with outputs here. Okay, and again, I'm going to stay with x being the input and y being the output. Just, it's keep things easier to stay with the tradition. So x here being the input. Okay, so now how about when x equals -1? Okay, then the outputs here -2. Okay, when x is 0, okay, the output here is -3/2. Okay, when the input here is 1, okay, and then the output here is -1, and you can always double check my calculation. So it's just another practice for us in a sense of, hey, we have a function here and we construct table of values by giving an input and evaluating the output, giving an input, evaluating the output. Like that. So when x equals 2, okay, when x equals 2 as the input for this. So x or y or whatever, it's just a convention about the input or the output. Okay, so in this function again, the function itself indicated that x is the input. So let's take it. But the idea now, if we take the input 1, if we take the value 1 for the inputs, the function comes out with the output -1. Okay, so and at this point, after you have seen and built enough experience with your function, and as I have explained long ago in much earlier lectures, the naming the input variable is not important. The point is, the rule here is of this function says for every input, we take away 3 first and then divide by 2, and that's how for each input here. Just because I call that x, okay, doesn't mean it have to be the same x with the earlier function. I gotta mention that a little bit. Okay, so now when input equals 2, we come out with output negative 1/2. All right, so these are a few input and output values again. Okay, so again, just nothing special about this function. It's just like any other function where you can get an input, and you can just give an input and get an output. Give an input, get an output. Okay. But now let me continue this function a little more with the table of values. So this table of values, I mean, technically I can stop here, but now let's just try to discover some connection between this function and the earlier function. Okay, so now let me do this. I'm going to continue. I'm going to really continue my table of values here. I've chosen these, and now let me continue this one here. How about when x equals 3? Okay, when x equals 3. We come out with y value equals 0. Okay, x equals 3, y value come out equals 0. Okay, just straight out the way how it's calculated. And then when x equals, now I'm skipping 4 now. So yes, you can get 4 in here, but I purposely skip 4. Let's look at 5 here. Okay, when x equals 5 right here. Okay, 5 minus 3. The rule says for every input we subtract 3, divide by 2, so 5 as the input, subtract 3, okay, that gives me 2, and divide by 2, that gives me 1. All right, and now let's choose 7. I'm skipping 6. You could have tried that too, okay. You could have put 6 and, I mean 3, 4, and 5, and 6, and 7, but I purposely skipped 4 and 6. It's just, not important, okay. I just get these here. They're just other input values that come out with corresponding output values, but I put these up for purpose, and they're all consistent with this rule of the function so far. So now when the input equals 7, we're coming out with positive 2. Okay, now I'm skipping 8, I'm skipping 10, I'm looking at 9 right here. Okay, it's just because these values here, once we're subtracting, it's easy to divide by 2, so I use them for now. Okay, so when the input is 9, we're looking at 3. Okay, and so now I'm even skipping quite a few values, and I'm looking at, how about 15 right here. I'm skipping 10, 11, 12, 13, and 14. Those, you can give them a try too. Okay, but now after skipping a few, I randomly chose a 15. 15 as the input. 15 minus 3 is a 12 divided by 2. That gives me 6. Okay, and then now one more input values, and then we're gonna start heading out into a different direction right here. So now when input equals 19 into this function, I'm gonna come up with output being 8. Okay, 19 minus 3 is 16, divided by 2 is 8. All right, so right now in your impression about this function, it's nothing but just another function. It's just another function. Okay. It has, just like the earlier function, we can give an input. It comes out with an output for us. And I just purposely went a little longer in this function in terms of the table of values. All right. But now, once I've finished constructing the table of values for this function g, I want anyone learning in this lesson to look at the following a little more closely. Yes, technically this is just a continuation of our table of values, and for these functions, it's impossible to look at every single value because it's a lot of values. First of all, now just similar to f of x, how about yes, I can see that this is a linear function, and you can verify me on that. In your experience of learning with me, at this point you should be able to verify that this is a linear function. Now, it has a domain. Its domain is from minus infinity to infinity. Okay? And then this is the next thing I want, just like for f of x, I want anyone learning in this lesson to verify, to verify me. This function here is a one-to-one function as well. Okay, one-to-one function. All right, so you can go ahead and pause the video and verify that for me. Just because, you know, don't just let your teacher tell you and then you're gonna just accept that as the way because your teacher tell you. Now, learning math, you have that quality where you can also verify, so that one day, hopefully, any one of you learning this lesson here will become a teacher on your own. Okay, so hopefully that you have already verified this is a one-to-one function. Okay, so now back to what I was in the middle of saying. Now let's focus on this part. It's just a part of your table of values, but I purposely extracted out. Let's look at this part right here of the table of values, and let's recognize something special about this. Now let me swing back to my other board. If we notice anything special with these. Now, for f of x, these values 0, 1, 2, 3, 6, and 8 right here, I use them as inputs. I use these values as inputs. For f of x, 0, 1, 2, 3, 6, 8, in this order, I use them as inputs. Okay? And now, these right here. At least with these limited within these values that I used on the board here. And then, those same values right there, now for this function g, they are the outputs. Okay? And now let's look at these that I circle. These values that I circle. These values are, in this function g, they are being used as the inputs. Okay? These values in this table, I'm using them as input. Now see, numerical values are just numerical values. But now for this particular function, I use these numerical values as input. For this f of x, for this g of x function. But then I circle them for a special reason. Let's have a close look and let's have a close observation of them. And then, let me now open back the other board. Those that I circle there, I use these values as the input of g. But those values we saw on the other board were the output values of our f of x. Okay, so the idea is now start coming out to light right here. The idea, we're starting to see some light about some connection between f and g right here. We're starting to see some light, some light is sparkling up about the connection between f and g, because here it looks like the inputs of f for the g function. For this g function, the inputs of f were the outputs of g. Okay, that's something we noticed. So let's write it down. I have a little bit of space here, so this is just some connection about the two functions that we observed. Some observations about the connection between the two functions. So I'm going to write it down. See, that's why the corresponding parts, I have to put them either with brackets or with circle. So the brackets part right here, inputs of f, these inputs or input values, right? Inputs of f, those are, in this problem right here, are outputs. Okay? Should have underlined that with red ink. They are outputs of g of x. Okay? Inputs of f. Outputs of g right here with the same brackets. All right, inputs of f are the outputs of g. And then these values, these numerical values, now being the input of g. Okay, let's see what they are again. So inputs of g, they are, or input of g, you just saw they were outputs of f. Okay, now I can just simply say inputs of g of x, okay, or outputs of f. I'm a little bit running short of space, so allow me to write things a little squeezy like that. So inputs of f or outputs of g. But then inputs of g, on the other hand, or outputs of f. They have that switching or flipping over nature like that. They have that going back and forth nature like that between the two functions g and f. Okay. All right. So now, ladies and gentlemen, that kind of relationship that we see right here, the inputs of f will become outputs of g, just there. And then any input of g, okay, was an output of f, okay, and that's what it's saying here. And so here in general, for the rest of the lesson here, it's all about we recognize this relationship between any two functions. Okay, so now allow me to erase the board and make some more space right here. And we're still looking at f and g, but right here in the way how I'm saying, okay. In the way how I was saying, I just now have to erase the input of f, okay, is the output of g, and on the other hand, any input of g is the output of f. Okay, so now first of all, in our familiar functional notation, we say that f of x, well, if x here is the input, if x here is the input of this function, then this is the input. Okay, so input of f comes out to g, comes out to the y value. Okay, and this is called the output, just like that. Now, back in my video lessons about one-to-one function, I brought in this convenience this convenient way to understand about function, that a function takes an input to an output. A function takes an input to an output. So just like that, if we take that same idea, we take that same convenience into this problem to think about the function, then f, okay, f takes this x inputs to y. Okay, f takes that inputs to y like that. But then now for the function g, according to the observation, what happened there? The input of g comes out being the output of f. Okay, if you see this variable y here being the output of f, and again, inputs can be any variable's name. Inputs can be any variable's name. The point of input and output is that just any function takes an input and it has a rule to apply on the input. So g, even though on my board here initially I wrote g with the inputs naming x, but when you're putting the two together, okay, the input of g is just whatever you take now according to the observation we've had. The input of g, okay, becomes it was the output of f. So that means if you're taking those outputs of f right here, these y's value, and then you give that into the g function. All right, that's why now these outputs right here, as far as the variable's name, we call that the y variable. But now, on behalf of the function f, the y value here is the output. But now to the function g, on behalf of the function g, the y value can be used as the input. Okay, and then it comes out. The function g takes input to y and comes back to x right here, which was the input of our function f of x. Okay. All right. So now we can see that, and now I'm drawing that arrow right here. F takes an input to an output y, an input x to an output y, and then if we give that output y to the function g, if we give that output y as the inputs to the function g, how's that? That's precisely the way I have to say. F, again, takes x to the output y. Takes inputs, we call it x. Whatever inputs, we call it x to the outputs y. But then after that, we take that output of f, but now giving that to g as an input. Then g takes that output, take that input, y value right there, coming out with an output. But now this output here become the input of f. Okay, so for g, this is the input. For g, this is the input, and this is the output. All right, but then it goes the opposite way. All right, it goes the opposite way. Okay, and then again, I made you realize earlier that both f and g, they are all one-to-one function in their domain, and they all have that domain easy to recognize from negative infinity to infinity. Okay, so now at this point, here's the term for each, the term that I first time being introduced here. So in that way, you see that again, that nature is the function f takes an input to an output, and then that same output from the function f here, once given to g as the inputs, then it's going to be taken back to x, back to that output. So x here is the output of g, but it was the input of f. So they're going, x gets taken to g by the rule of f, but then y is taken back to x through the rule of g. There are so many ways of seeing that, but in the end it's going the reverse way. You're going one way and you're going backward. Okay, so you can think of this as f is going forward and then g is taking the values backward. Or if you're looking at g as your main function, then g is going forward this way and then f is taking things backward. Okay, and so now in that way, ladies and gentlemen, okay, you can now say in this chart right here, now you can say g is all right, g of x is the inverse, precisely inverse function. All right, it's the inverse function of f. And now putting the variable's name here is just nothing but just confusing. So I'll just like, hey, the rule g is called the inverse function of f. Input can be named whatever. Okay, so g is called the inverse of f. So think about it. So that means vice versa, because the way how the chart here is indicating. So if you're treating f as the forward function, then g is going backward. But you can also treat g, as I said earlier, you can look at g as the forward. This arrow right here, you can look at g as the forward. Then f of x relative to g will be the backward direction right there, bringing every output of g back to where its input was. All right, so in that way, I have another equivalent statement. And these two statements are always equivalent. So on the other hand, f is the inverse function. F is the inverse function of g. So g is the inverse of f, then vice versa. F is also the inverse of g right there. All right, so that's the understanding now. So we are at the very beginning level, and there is a whole world for people learning specifically about inverse functions. Okay, so it will be impossible to learn everything about inverse functions. It's impossible to learn every detail about inverse function here at this level, but allow me to introduce what's understandable enough for the pre-calculus students. Okay, and then even in your higher courses, if anyone plan to get there, in your higher courses, even beyond calculus, you will keep recognizing more and more fascinating details about inverse function. Okay, and like I said earlier, there is an entire world, an unlimited world of inverse functions out there. Okay, a whole world of details about inverse function that the more you look into it, the more it will come out. But for now, in this lesson, I will only introduce what's understandable enough. Okay, and so now, in the way how it is right now, if g is in that relationship we recognize, and I drew that in this going around diagram right here. Then g is called the inverse function of f, and f is the inverse function of g. On the other way of saying. Now let's get ourselves ready into a formal definition. And then keep in mind, before I even hit to this important point about pointing out the relationship that f and g are inverse of each other, that's another way of saying f and g, they are inverses of each other. Okay, but now before I got to that point, pointing out the connection between f and g, then I was mentioning clearly f was a one-to-one function and g was also a one-to-one function on their own domain, like that. Okay, so now, all right, so let's get ready for tackling down the actual definition, the formal definition in worded. Okay, in worded definition, the definition of what it means by, one function is being the inverse function of the other one, and then we're going to also along the way come up with the formal notation. Okay, because earlier that was just in statements like that. So now as a definition. Okay, so as a definition. So now I'm going to allow me to write. I found this definition from a textbook that I'm using. Now I aim that my lecture here is independent with any textbook like that, because it's worded slightly different from it's not exactly a copy print of any textbook, okay? Because I have my style of organizing the material, so the material should be found in any textbook. And then here and there, if I find this textbook has this particular definition that really, to me, I like it, it clicks for me good, and then I want to pass it on to my students, and I use this. But that doesn't mean all of my lecture based on this one particular textbook or that other one particular textbook. So I found this definition through a textbook, okay, through one textbook that it really caught my attention right here. So now allow me to introduce it as following. So now I'm going to say, we're going to start out with, this is crucial to start out with this line right here. And that's why I like this definition given in this textbook. Let f of x be a function, okay? Let f of x be a function that is one-to-one, okay? So we start out for easy level, at the easy level for beginners to catch strictly requirements. We have to have the function being one-to-one before we can find inverse, and I'll talk even more about that. And you can see in my work already, I asked any one of you viewing this lesson to check if the function was one-to-one before I even point out that connection between the two functions. Okay, so now it exists right in here in our definition. So let f of x be any functions, but that is known to be, that is one-to-one on its domain, okay, on its domain. See, I also talked about domain earlier. So right now we just need to keep this as a crucial requirement before we even shop for inverse functions, before we even recognize inverse function. Okay, so let f of x, any f of x, be a function that is one-to-one on its domain. Okay, then now in that case, once we have our function f of x satisfy that requirement, then now the function g of x, okay, basically, see, it's a different function. An inverse in the end, it's a different function. It's not the same function as f. That's why we have our legal way to name it a different letter, because it's not the same function with f. Sometimes it's the same. I'm not saying that it's always have to be different, but sometimes it could be the same. But in the end, you can see that it's a different function that we're working with. Okay, so now the function g of x is the inverse, and now let me highlight this term in red ink. The inverse function. Okay, so any function g of x can be called the inverse function of f of x. Okay, if g of x satisfies. All right. G of y equals x exactly when I just realized I didn't leave enough space for myself. So satisfy g of y equals x. Okay, exactly when, that means only whenever f of x equals y. Okay, and then let me put an and to this definition here, and then I will, now this actual definition from that textbook I said that I use, it includes the statement I'm about to say in the same definition as well, but now in my lecture style allow me to break that later detail in the definition there as a separate remark. How's that? So now in this formal definition, let's keep it right here. This bottom statement right here is important. G has to satisfy, anytime we want to say G is the inverse of f, G has to satisfy, it takes the inputs y to x. But see this statement right here, exactly when, so G of y equals x, exactly when f of x equals y. What does that mean? That means, back to this chart, and like what I was stating out earlier, you see, that means if G takes the if G takes the value that was the output of f, if G takes a value that was the output of f, then it's going to bring that output of f back to the input right here. Okay, that's why I see G of y equals x. So relative to G, then the y value is the input. So if we take the y value that was the output of f as the input for G, then that value is going to get taken to x, which was the input of f of x. That's the idea right there. And that's what it means in the precise term. G of y equals x exactly when f of x equals y, because see, when f of x equals y, that means y here, this same y value is the output of f. But then in the role of G brings that output of f back to that input, because x was the input of f. That's why G is said to be the inverse function of f. Sort of like G is the going backward. So f took that input x to y. And that's why, like I keep mentioning about that convenience, about that convenient way to understand about a function. This function f takes the input x to y, the output. So now for inverse, G as a separate function, but it's playing in the role of, it takes every output of y back to the input. That's what it is. Okay. So the output of f, once given as the input of G, it will be taken back to the x value, the input of f. All right, that's what it is. That's what it is. I don't want anyone learning in this lesson to just rushly take that definition and then be done with that. Nope, that's not what it is. Pause the video, or even if you feel a little too much, exit out of the video, but keep thinking about what I'm saying. Okay? You got a function f. It takes x as the input and come out with an output, as we already knew. But now all of a sudden I introduce the inverse. So what's the inverse? I mean, the inverse in the end is a function. It's just a function like any other function, but now relative to f, related to f or connected to f. It takes every output of f and bring it back to the input of f. That's why G, once taking y value, now remember, remind yourself, y value was the output of f. But now once you give the output of f as the input for G right here, that y value will be taken to x. X right now is the output for G, but it was the input of f. That's the one more time I'm saying it. Okay, you can feel free to pause the video or even exit out of the video to keep reminding yourself every word I was saying here, because it's such a big concept that here, of course, I only introduce in a way that understandable enough for any student, but this is the building block for the entire world of inverse functions. You will see this concept of inverse function again later at the later end of the quarter of the learning term with me. You will see this concept about the inverse function again when you go on to a course that normally referred to as calculus, pre-calculus 2, or in many other schools around the nation call that the trigonometry course. Okay, and then when you go to calculus courses, you will see this concept again. Okay, and then when you go to even courses beyond calculus, you will see this concept again, the idea about inverting. Okay, taking the inverse. The function takes an input to an output, but we want to come up with a different function that takes an output back to that input. Take this value that was an output back to an output that was an input. That's the idea. We're going backwards. All right. And so now, at this point, assuming you have had all of your time pausing all over the video to digest every word I'm trying to deliver here, okay? And then had for yourself a decent understanding enough so that now, assuming that you have had all of that time spent on understanding this, and let's advance on. So here, I want to start getting into a couple practical things with inverse function. But now I have to emphasize, I said this earlier, in order for a function to have an inverse. So having an inverse it's not an automatic thing, okay? Some function, a lot of functions have inverse, but some functions don't, okay? And so to make it easy for starters, for beginners, let's set our rules here. So right for now, I'm asking anyone as part of this definition here, I'm asking anyone to take this part as a requirement. That's why I said that earlier. We're only working with, in order to, anytime we're about to talk about inverse function, or even before we find the inverse function, which later on happened as example problem, even before we find inverse function, we have to make sure that our function at start is a one-to-one function on its domain. Okay, so for now, underline this and keep that as just a requirement, a prerequisite before you start looking for inverse function. Just find that use that as a prerequisite before we can look for inverse function. Okay, so your function, if you want to start looking for its inverse, okay, let's call that. Let's make sure that your function is a one-to-one function on its given domain. That's one more thing I would like to point out right there. All right, and then so now, at this point, another remark I would like to point out right here. I will get back and talk even more about this, but you can see that. So when we talked about domain and range earlier, of course at that time, we just recognized the domain as the set of possible input values for the function. And then the range was the set of possible outputs value that came out from a function here. But then that was it. We spent some time learning to find the domain and finding the range. That was mostly what we did in that lecture there. Okay, but now let's see that when we get to inverse function, after you also learn about what function is what it means by being a one-to-one function, the idea about domain and range becomes even more important. So now I want you to realize one more thing right here. You see, so assuming that any of the input here for f, let's just start out with f right here. F is some function. It takes an input x and takes it to an output y. So x here is in the domain. Okay, so x here, of course, is in the domain of the function f, and then y here is in the range. Okay. So in that way, and allow me to still keep this chart right here. So right from this, so x and y, at this point, they're now just values, numerical values. But so x is in the domain of f of x. And then y, any value y here is in the range, okay, of f. But now the same two values, x and y here, if you're looking at them as a pair of values from g function right here, then y is here, y here. See, because every output from f of x is now the input on g of x, on the g function. And so now if f and g are inverse of each other, okay, if f and g are inverses of each other, then the y value is in the domain, okay, in the domain of g. Okay, and then these are bullets items right here, and then x relative to the function g, x is in the range, all right, of g. That's another thing I would like to point out right here, according to this chart. And so now that's why, now back to that other board where I was writing down the definition of the domain. Now I can put in that remark right there as a remark. So this remark was part of the definition in that textbook I found, but I found it's a little too much all of a sudden at one step just throw in every single worded line to your attention. So I talked about the main core thing of the domain, I mean of the definition, and then I talked about the domain and range property of inverse function a little bit, and then here we put that as a separate remark. Okay, so now as a remark, once you understand what an inverse function of a function is, then I'm going to say that if g is the inverse of f, then the domain of g is the range of f. All right, because it was that idea, like I was saying, once we recognize that g is the inverse, then that means it's related with f in a way that it takes every value in the range of f and bring it back to where where y value came from. And so in that way, every output y value of f, which is in the range, every value in the range of f is in the domain of g, ready for being taken back to where x was, where the x value was. Okay, and then now on the other hand, on the other way around, the range of g, okay, is the domain of f, because again, the purpose of g is to come out with to take an output of f, to take a value that was an output of f and bring it back to those values being the input of f. So that's why the range, so whatever comes out from g is the range of g, but the range of g serves purposely as the input of f, and that's why the range of g is the domain of f. And that's another, these two statements enhance our understanding about the inverse function, the inverse of a function. Okay, all right, and so now this board of mine is getting a little squeezy now. Okay, allow me to erase the information there, and then I'm going to start introducing a notation. Okay, so all right, so now as far as notation, you see, so assuming that the function f here has g as its inverse, okay? assuming that the function f has g as its inverse, then see, if f of x has g as its inverse, then instead of using g, because eventually what I pointed out earlier is that being an inverse, in the end it's a separate function. It's a function separate from f. They are connected, but it's separate from f. It's a different function. So in the end, if we keep using a different letter's name, eventually we're going to run out of letters name. Okay? But then we want to point out that specialty. I mean, it's a function, it's a separate function away from f, but it has some relationship. So we want to come up with a notation that rings a bell for any reader. For any reader that, hey, it's related with this function through the inverse relationship. Okay? And so in that way, we're going to come up with the following. So this right here, instead of calling that g of x, instead of naming that g of x, we're going to name that with the following symbol. F with a superscript -1 x. That's make it clear right here. So now if f is some function, then f with the superscript 1 right here, we call it's f inverse. Okay? It's the f inverse of x. So, or it's the inverse f of x. That's another way of saying. Okay, you read inverse f, okay, of x. So that's just the input parameter. This is indicating that it's the inverse of f. Okay, and sometimes people also say that symbol right there, f inverse. Okay. Of x. They're using terms a little loosely, I agree. Okay, but then instead of calling this g being the inverse, they're gonna just come down with that symbol right there. Okay, it's just that simple. So now, on the other hand, once f of x has an inverse called g, and we recognized that earlier, once g is the inverse of f, then f is also the inverse of g. Okay? We have read and agree on that. So now if g has f as its inverse, and now in that way of how we're understanding we're gonna, instead of calling that with a different name, with a different letter, we're gonna use g with the superscript -1. All right, so now you're gonna start forming into a pattern about how we use a notation here. This is just a notation. It's a notation. It's indicating it's the inverse of the function f. But in the end, it's a function. Instead of calling that g or h or whatever, we call that with this special name to know that, hey, this function here relates to our main target function as the inverse relationship. So same way here, if we're treating g as the main function, then its inverse, we're going to use the symbol, just the notation, g with the superscript -1. Okay? And then, yes, this is just, again, the notation. Instead of giving that a brand new name, Okay? Now I have to also clarify, this does not mean it's just the symbol. I keep having algebra students of mine, pre-calculus students of mine, and even calculus students of mine mistaking this. So I gotta point it out before it's too late in your later courses that you recognize that in the wrong way. You see, it's -1 superscript. Some people see that as a 1 over the function f of x. That's not the case. It does not mean 1 over f of x. It's not the reciprocal. Yes, admittedly, in algebra, a big amount of times we're using -1 superscript as a power -1, and power -1 means it's a 1 over that quantity. Okay, it's the reciprocal, but here it's not intended. This symbol is not intended as the power -1 of f. Nope, it's not the power -1 of f. It's one symbol here as one package. It's the f inverse symbol. Okay, so just like that, this is the symbol for G inverse, the inverse of G. Okay, G with the superscript minus 1, the symbol right there. But it does not mean it's not, this is not 1 over G of X, okay? Or it's not even G to the negative 1 power. Don't say it that way. It's going to lead you into a serious misunderstanding. Okay, so that's about inverse function. Okay, so now at this point, after talking and diving in so far into some of the theoretical details, and again, believe me, this is just what's enough for us to understand and move on fluently within our class understanding. Okay, there are still a lot more details about inverse function that have to wait until you advance even higher than a calculus course, like that. Okay, into a much higher course. There, like I said, there's a whole unlimited world of inverse functions out there to study about. All right, so let's now erase the board and look at some example. All right. So I've talked about this earlier, that I want you to understand in this definition here, I want anyone learning in this lesson to understand that right now, taking function, working on one-to-one function and working on those functions being one-to-one on its domain, that's a prerequisite, or it's a major requirement for finding inverse. Okay, so you gotta be working with a function, with a one-to-one function, in order to find it in its inverse. Okay, so now it comes to the following kinds of problem. Example 1. Okay, we want to determine if each of the following functions, all right, is or each of the following function will have an inverse. Okay, because now sadly not every function has an inverse. So inverse, yes, it's a function. Inverse function itself is a function. Inverse function itself is a function. But then, if you're now starting with one function before you even find its inverse, and I haven't talked about how we can find the inverse yet, but before we can talk about finding it, we have to have a way to ensure that the function will have an inverse, so that we won't waste our effort finding it and then it's not there. Okay, and so now, yes, it's that kind of problem where now I'm going to be giving you a list of functions. Okay, and we're going to determine, hey, is this function going to have an inverse or not? Is this function going to have an inverse or not? Or is that function going to have an inverse or not? Okay, so now that list here, about check all that apply. Okay. So these are the functions now. All right. So now in this list right here, our first function on the list, we have a function being x to the power 11. Doesn't have to be a function that you have already known, okay? But then, and then allow me to complete my list, and then we're going to go through the list and find and check to see if each function here among the given functions here has an inverse or not, okay? So now, how about if the function can be a different function here? How about minus 5/3? All right, and then there's another function here I have on my prepared notes being absolute value of minus 7x plus 12. All right. And then my list is not done yet. Let's look at f of x equals x squared minus x plus 1. Okay, and I have another one here being about f of x being cube root of x. All right, so these are some functions that we want to check to see if they have inverse or not. So why is there such kind of problem? Because think about it again. If we're looking back at this definition one more time, it only gives the definitions. The function g of x is the inverse function of f if it satisfies, right? So that means, think about it. If our function fails to be one-to-one on its domain right here, okay? Okay, so think about the way how this worded definition is. This definition is worded. The function g of x, it's a separate function from f, is called the inverse function of f if it satisfies. So think about it. There are so many functions out there aside from our f of x function, okay? And then if it satisfies this requirement right here, then it can be an inverse. It satisfies this requirement, it can be an inverse. And so think about it, there could be cases that aside from your f of x function, no other functions satisfy this requirement. So it brings up that concern already about will a function f has another function satisfying this requirement or not. So that means we're talking about existence of the inverse. For a given function here, will we be able to find that other function satisfying this description? That's why we want to look at that kind of problem right there, where will we have an inverse function or not? That's one thing to see right there, to point out that, hey, there could be time where your function does not have an inverse. There could be time where your function does not have an inverse. Okay? And then now look at even the more important one. Right now, I ask any of my students who view this lesson to see only this as a requirement. You see, this definition here, this part of the definition, this starting part here comes after this prerequisite description. So we have to have a function f of x being one-to-one in order to talk about those function g's that satisfy this requirement, that satisfy this description right here. So even getting into the description of a function g, we have another prerequisite. Your function f of x at start has to be a one-to-one function. That's even more crucial. Right now, I'm holding on to the explanation why we need to have that function f of x being the one-to-one, but one-to-one is the first requirement. If your function in the beginning fails being one-to-one, it won't have an inverse. It won't have an inverse. Okay, and that is the reason why this lesson here is extremely beneficial if you're watching that after you have watched my lecture about what a one-to-one function is, because now I'm not going to be worrying about this description, because we can find that a lot of time we can find the function that does this description right here, that satisfies g of y equals x exactly when f of x equals y. A lot of times with a given function, we can find another function like this requirement. But the more important requirement is right from that starting function, was it a one-to-one function or not? That's the deciding line right there. That's the deciding criteria for having an inverse or not. Okay? So now the reason now I mentioned this in clear, the reason I mentioned this clearly and bring that down to details right here, because in this particular problem, surprisingly, all we have to do, even though this is a lesson about inverse function, but the only way to determine if this function, for example, has an inverse or not, the only way to do that, check to find out whether this function is a one-to-one function. One-to-one or not. One-to-one or not. 1-to-1, yes, it will have a function. I'm not saying 1-to-1, yes, it will have an inverse. Okay, I'm not saying how will we find that inverse. I'm not saying that yet. I didn't get there to teach that part yet. But 1-to-1 means it will have an inverse. Not 1-to-1 means it will not have an inverse. Okay, and then the same way right here, this function as a separate one. If it's a 1-to-1, yes, it will have an inverse. If it's not a 1-to-1, it won't have an inverse. So now really all of a sudden we realize this example brings us back to that kind of problem where we just simply have to decide whether or not any one of these functions in the list here is a 1-to-1 function. We just want to decide whether or not this function is a 1-to-1, or that function is a 1-to-1, or that function is a 1-to-1 or not. All right, so that's all there is. So as an intention behind the scene here, now in these modern day, in these days of the 21st century, where we have technologies all over the web, and you have your own calculator, you have your own calculators to use that are quite advanced, then feel free to use your technology to pull up the graph instantly, okay, and check for and use the horizontal line test to check for 1-to-1, and I have shown that that particular technique back in the lecture where we talked about 1-to-1 function. Okay, and so now let's one by one look at the graph. I'm going to use, so it did not need to be mentioned here, but I'm just going to use a graphing utility or a graphing calculator to put in the graph of any of these functions. So we're going to look at the graph for each one of these functions one by one, and then use the horizontal line test to decide, hey, is this one the 1-to-1? If it is, I'm going to put a check here saying that it will have an inverse. If it's not, we're going to skip the check mark here. And then we're going to move on to the next one on the list and the next one on the list. That's how we're going to work through this particular problem like that. All right, and so now on my graphing screen right here, this is the graph for the function f of x equals x to the 11. Okay. It looks almost like a cubic function, but it's a lot more flattened down right here. Okay. All right, so here's my horizontal line. All right, so now I'm gonna, just like that technique, that method I showed from the video lecture about how to test if a function is a 1-to-1 function. I'm gonna be tracing I'm gonna be bringing I'm going to be sweeping my horizontal line up and down to make sure anywhere I place my horizontal line there is no more than one crossing point. Okay, so it's starting to get a little dangerous because it's hard to tell from afar, because when I bring the horizontal line to about anywhere near the x-axis, it seems like the horizontal line align with this portion of the graph for an interval, but actually it's not. Okay, as I zoom in, let's say right at 0.5 right here, as I zoom in, okay, right at 0.5, as I zoom in right here, there will be some difference coming out. Okay, so in other words, my point I'm trying to prove here is that no matter in this way how the graph is, even though it looks quite flat out here for our x to the 11, okay, but this horizontal line still only crosses the graph at only one point, anywhere on this line right here, anywhere on this graph, vertically. Okay, so as I bring it up, vertically it's only crossed the graph at one point. Okay, and I can zoom it out further so that we can have even more complete, a better complete view of the graph. Okay, so it's 1-to-1 and it's 1-to-1. All right, so it passed, in other words, my line here, my graph here for f of x equals x to the 11 passes the horizontal line test. And so it means this function here is a 1-to-1 function. And so consequently, being a 1-to-1 function, it already met that requirement. It's 1-to-1 on its domain right there. Okay, and so now, will we find this function or not? This part of the definition on the inverse function, that's up to how we can find it, but I guarantee you it will have an inverse. Okay, so as long as our function is recognized to be one-to-one. And so now I'm going to put a check mark here. All right, I'm going to put a check mark there. Okay, so now let's look at this function. Let's look at that function. F of x equals negative 5/3. It's a constant function. It's a constant function. All right, and in our graphing space right here with a graphing utility, this is the graph for f of x equals negative 5/3. Negative 5/3. So it's a one constant flat line. Okay, so now I'm going to use a horizontal line test again. So now be aware of one thing, that this function right here that you are seeing, this function you are seeing is a one horizontal flat line right there. So the range of that function is only one single point, negative 5/3. That's the range. One single value on the y-axis right there, negative 5/3. Okay, but now we want to find out if this function is a one-to-one function or not. Okay, so now we're going to place a horizontal line. So I'm going to be moving my horizontal line up and down right here. Okay, so right now the horizontal line still did not interfere with the graph of the function yet. Okay, but now I'm going to bring that right into 5/3. Okay, so now the graph itself is a horizontal line, and now this line in dotted ink right here is in dotted black ink is also a horizontal line. So once they are placed exactly on spot, once the two lines are placed exactly on spot with each other, okay, then they're crossing each other at infinitely many x values. They're crossing the dotted line in black color and the red line right there. You can see on the graph. Okay, you can see on the graph right there. That's why we have kind of like an overlapping of the picture right there. Okay, so the horizontal line and the horizontal line being the graph, they align with each other infinitely at many points. At infinitely many points. And so in that way, this function, this constant function, any constant function, fails to be one-to-one. Okay, because at this only outputs value, at this only y value, there are infinitely many output values that come up to that y value. Okay, and that's the reason. And so this function f of x equals minus 5/3, in other words, fails to be one-to-one. It's not a one-to-one function. So now what it means for us here, this function, I'm skipping the check mark here for this function. It will not have an inverse. It will not have an inverse. Okay, let's now move on to the next one right here. So once again, we've been doing two problems. It's all about we're checking if our function is a one-to-one function or not. Okay. All right. So now back in my empty graphing window, this is the graph for absolute value of minus 7x plus 12 right here. Okay. This is the picture of that graph. All right, and so now once again, in order to have an inverse, this function needs to be one-to-one. In order to have an inverse, this function needs to be one-to-one. So let's find out if it's one-to-one or not. Once it fails to be one-to-one, it won't have an inverse. And so now the only way to find out, I'm going to use a horizontal line test again. Okay, so here's my horizontal line test. All right, so right now the horizontal line the horizontal line is not even interfering with the graph yet. Let's keep moving it up. But now, as soon as I put the horizontal line test to interfere with the graph, I already found a spot where this line crosses with the graph at more than 1 point. So that's right there is enough to prove that this function in red fails to be one-to-one. It's not one-to-one. This function is not one-to-one. So in that way, f of x equals absolute value of minus 7x plus 12 will not have an inverse function, because we want to determine if each of the following functions will have an inverse. The first one will have an inverse because it's one-to-one. We verified that through the horizontal line test. The second one failed because it's not one-to-one. It was not one-to-one. We saw that on the graph. The third one just now also failed because it's not a one-to-one function. So all it matters, being one-to-one means it will have an inverse, and the other way around. Okay, having an inverse also means the function has to be one-to-one. Okay, so that's the only criteria to check with that. All right, so now let's look at the next one right here. F of x equals x squared minus x plus 1. All right, in my empty graphing space again, this is the graph for f of x equals x squared minus x plus 1. Okay, and I am now going to put in our horizontal line. All right, so this is our horizontal line. Right now it's not interfering with the graph, but once it's interfering, we immediately see that pretty much anywhere throughout the range of the graph here, the horizontal line will cross with the graph at more than 1 point. And say right here in this picture, we already have that. And as a matter of fact, if we're looking at the horizontal grids right here, any of these grids crosses through the graph at 2 points, at more than 1 point. Okay, so in that way, now it's clear that this function, x squared minus x plus 1, is not one-to-one. So now failing to be one-to-one means this function will also fail having an inverse. It won't have an inverse. So what it says here is that don't even waste your time and your efforts to look for an inverse, to look for the function that satisfies. So don't waste time to look for the function that satisfies this, because we won't be able to find it. It doesn't exist out there. Okay, on that function with its domain that way. Okay. And now, since I'm talking about domain a little bit, see the domain of this function, and you have seen that throughout lecture of learning about domain and range. Then the domain of this function is the entire line of real numbers from minus infinity to infinity. So in the domain of this function, then it will not have an inverse. Okay. All right, so now let's look at the last one on our list. F of x equals cube root of x. And once again, the only way to check in the domain of this, okay, or in the viewing window of the graph right there, is this function one-to-one. Okay, that's all it matters. Having an inverse or not means the same thing as being one-to-one or not. Okay, being one-to-one, yes, it will have an inverse. Not one-to-one, it won't have an inverse. So these were not one-to-one. That's why they didn't have these functions here. I put a cross there. They didn't have inverse. Let's check this last one right here. All right, and now this is our cube root function. All right, this is the graph for the cube root function. And the domain for this function is the entire line of real values right here, or in interval notation from minus infinity to infinity, the horizontal spreading of this graph. Okay, so just want to briefly mention about the domain, because now in its domain right here, now I'm going to put in a horizontal line. Okay, and we're going to find out throughout its domain, will this horizontal line cross the graph at any value? All right, I mean, will this horizontal line cross the graph at more than one value, more than 1 point in its domain, in the domain of this function? And so now anywhere up and down that I'm sweeping my horizontal line, it's only crossing the graph at 1 point, 1x value in the domain of this function, the cube root of x. So in that case, as a final conclusion, this function here, as a conclusion, this function is a one-to-one function. And now being one-to-one function, yes, this function will have an inverse. Okay, we haven't learned how to find the inverse yet, but then this function here, we know for sure if we are spending our effort to find it, we will be able to find it because it will be out there. Okay, so this one here will have an inverse. All right, so that's how we can determine that if any of these functions can have an inverse or not. So mainly it is all about we deciding whether this function or that function is a one-to-one function or not. And the only way to check for one-to-one function, use a graphing utility. At our level here, you are welcome to use a graphing utility. Okay, and then use that, and then use your graphing utility to put in a horizontal line. And as long as the horizontal line, as long as anywhere you place your horizontal line cross the graph at only one point, okay, it's a one-to-one function. Or otherwise, if your horizontal line cross the graph at more than 1 point, it's not one-to-one. So one-to-one means it will have an inverse. Not one-to-one means it will not have an inverse. Okay, that's all there is for this kind of problem. All right. All right, and so now that we have learned how to quickly determine and how to quickly decide whether a given function will have an inverse or not. Okay, so now that let's put ourselves in that scenario where we have already decided this function will have an inverse, or this function is already a one-to-one function. So now the next stage here, the next exciting point, the next important step now is how can we find that inverse? So now we knew, again, as I'm saying, we already knew that we've learned that skill how to verify if our function will have an inverse. So again, let's say we have a function and we already knew, after we already knew a function, this function we're working with has an inverse, will have an inverse. So how can we find that inverse? Okay, and so now allow me to bring up a demonstration problem, and along the way I would like to show a general guidelines for how to find the inverse. Once we knew, again, anything we're about to learn at this step and on right here, anything we learn at this point and on is always after we have already knew that the function will have an inverse, or the function has an inverse. So here I'm going to show how to find that inverse right there. Okay, and so gladly there is a good general guideline, and it works anywhere. Okay, once we knew that our function will have an inverse, then we can apply this general guideline here. So first, let me bring up this demonstration problem. Okay, so we can stay right in that problem I brought up earlier in the lecture right here. So now let f of x be that function 2x plus 3. Okay, and I was using this function as that the promoting problem, as that the introductory problem to introduce anyone into the idea of having an inverse function. Okay, and so now let's quickly look again. This function here itself is a one-to-one function. Okay. And to quickly double confirm the result I have explained about this function. All right, so here we are. This is that function that we're looking at. Okay, the function f of x equals 2x plus 3. And so knowing that it's going to have an inverse or not depends entirely on whether this function is a one-to-one function or not. And so we throw in that horizontal line test. Okay, so the line test here, as I can bring the horizontal line up and down as I sweep through the vertical spreading of our graph. Anywhere I place my horizontal line, the horizontal line only crosses the graph at 1 point. And so in that way, it confirms that this function will have an inverse. So we know for sure, yes, f of x will have an inverse. Okay, so that's one thing for sure. So we don't, logically speaking, we don't find the inverse. We don't find the inverse until we have already verified that this function will have an inverse. Otherwise, if it fails to have an inverse, our work to find the inverse will become a waste right there. Okay, our attempt to find the inverse will become a waste. So we only find the inverse after we already knew that the function will have an inverse. So take my words clearly on that. Okay, so I know for sure based on my horizontal line test to check for one-to-one. So one-to-one is the only criteria deciding whether a given function has an inverse. And so now we just now saw how I proven it. This function has an inverse or will have an inverse. And so now, in the earlier part of the lecture where I introduced the concept of inverse function, you probably already still remember that function g of x. Okay, that function g of x equals x minus 3 over 2. That function is the inverse of f. Okay, but see, the question, our goal now is that how did we come up with this function? How did we come up with this function? And yes, admittedly, g of x was the inverse. See, now I use that symbol. This is f inverse of x. So g of x that we worked with there, I also brought this up when I was showing table of values earlier. We knew that this was the inverse. So g of x equals that was the inverse, okay? Because we already talked about that. And then, so yes, formally speaking, it was that f inverse. That f with the superscript -1, the symbol over here. Okay, but now, how did that function come out? I mean, how did we find that function? How did I find that function to show it in this lecture over here? Now let me really tear it down to every single detail over here. So now we're going to roll back to that step where if it was me in the earlier point when I was preparing that lecture, how did I get that g of x as the inverse for f? Okay, and so now our goal here is to clearly find f inverse. Okay, so now allow me to start legally use that symbol over here for the inverse of f, or the the f inverse. Okay, f to the f superscript -1. Okay, and so now the logic again. A lot of time the worded instruction is simple. Just simply find f inverse, but it really intends that you have to verify whether your function will have an inverse first. And the intention here is that it's already kind of intentionally telling you that the function here would have an inverse. So all you have to do is find that inverse. Okay, so now, so let's start out writing down our function. Now allow me, as I'm getting into this, allow me to show the guideline at the same time. So 2x plus 3, f of x equals 2x plus 3. That's first step, just to write it down. Okay, I mean, this is actually not even first step. This is just a preliminary step. How's that? So just write it down on a separate piece of paper. And now I'm going to pull up that general guideline, the step-by-step guideline. And like I said, the good news is that this step-by-step general guideline will work anywhere. As long as you know your function will have an inverse, then we apply this step. It's going to always guarantee the correct, inverse function. Okay, so now, all right. So now, first step being brought up here. In this curtain, see. So now I was just saying this function notation right here that which we have learned long ago when we've learned about function. And this functional notation. Now I am going to purposely write that in equation notation, meaning see, step 1 right here, we're going to replace the f of x symbol with the y variable. Okay, and y or z or t is pretty much our choice of the variable's name, but see, the point of this step 1 right here is to write our function here in equation notation. So here, I just decided to stay with the traditional the variable's name x for the input and y for the output. That's why the guideline here in step 1 say we're going to replace the f of x notation or the f of x symbol with the y variable. All right, so that really, this is my first step right here. Step 1, I'm going to rewrite my equation as y equals 2x plus 3. That's it. That's it for step 1. Okay, so I'm breaking it down and I'm moving really side by side with the guideline right here. And now once we've got step 1 done, let's move on to step 2 right here. All right, and now with step 2, and I have to apologize for keep swinging back and forth because I have that note that ran on my computer station, so I have to pop it out right here. So step 2 now, look at the words right here. We want to interchange x and y. Because right now, at this point right here, after step 1 done, we have y and equals an expression of x. So now we want to interchange x and y. The real idea now is we want to swap row, we want to switch row of x and y. X becomes a y and y becomes x. That's what interchange means, okay? So in this equation, x becomes y and y becomes x. That's what interchange x and y means. So right now, I'm going to perform step 2. The y variable on the left-hand side, and that's the only place I see y variable. Any y variable is going to become x. So now it's x equals. And now any x variable from step 1, from the previous step, now becomes the y variable in our equation. in our current step. So now it's 2y plus 3. That's what step 2 is saying. Interchange x and y. All right, so we got step 2 down. We just now interchange x and y. All right, so now I'm gonna swing over to my station and pop out the next step right here. All right, so now this third step, at this point, I'm treating this equation in step 2 as an equation that has x and y. See, was also an equation, but this is now an equation expressing x as a function of y, as an expression in terms of y. So now in the third step coming right here, I would like to solve for y, and this is a skill where you should have learned that from your previous algebra course, anywhere from elementary algebra up to intermediate algebra. Before you enroll into this course that's called specifically the pre-calculus or the college algebra course. This is where we learn all the good details, all the apply ideas, okay, of all those fundamental skills you have built throughout your elementary and intermediate algebra courses, okay? And so if anyone experience difficulty with this solving step right here, it's a big step, I agree, okay? But and anyone either you're learning from me or public viewers, anyone that's struggling with this particular step, I highly recommend that you get a hold of your instructor. That could be me or that could be anybody else that assigned this video for you to learn from. But in the end, you need to get a hold of your instructor to get somehow a review on this kind of skill right here. We solve for one variable of the equation. We solve for one variable in terms of the other equation. We rearrange the equation, okay? So now from this equation, I am going to subtract 3 from both sides. Okay, so how about I'm going to take this space here as my scratch. Or as a matter of fact, I am going to take the other board as my scratch. Yeah. All right, so my equation at this point, x equals 2y plus 3. Okay, and even though I'm saying this is scratch work, but you are more than welcome to also embed this scratch work right in your formal steps as well. Okay, it just I was a little narrow in space, so I didn't write it down on my other board. So to solve this specifically, I am going to subtract 3 from both sides, and also I hope this is also a brief review of how you're doing this. Anytime we're having an equation, we can always subtract a value, an expression from both sides of an equation. So doing this, I'm going to consequently end up with x equals, x minus 3 to equal 2y. But I have not solved for y yet, because when it says solve for y, that means we purposely want y to stand by itself on one side. Y stands by itself on one side. So right now y is already on the right hand side. So we want y to stay right there, but by itself. Meaning just y equal. No 2, no 3, no coefficient, no power. Just y. Y equals. And then the rest on the opposite side is in terms of x. That's what it means by solve for y. Okay, so now let's get to it. So from here, in order to get y standing by itself, because right now it's 2 times y. So to have y standing by itself right here, to really solve for y as the final step, I am going to divide both sides by positive 2. Okay, because simply now dividing both sides by positive 2, that operation will cancel my 2 on the right hand side. Now I have achieved y equals, the left hand side now consequently would come out as x minus 3 all over 2. All right, so this is how I have solved for y. So in other words, y equals x minus 2. And this is that final step where I can bring that into the end result of step 3 like that. Okay. So now back into this board of mine, step 3 where it says solve for y. Now, so solving for y from this equation in step 2, I ended up with y equals, and now at this point we have our right to rewrite that in the traditional way where the main variable we solve for is on the left and everything else is on the right hand side. So y equals x minus 3 over 2. This is the end of step 3 over here. We have just now solved for y. And again, solving for a variable from an equation means we try to bring that equation, we try to rearrange that equation to the form where we finally have the main variable that we're solving for stands on one side, okay, and then on the opposite side it only has an expression entirely in terms of the other variable, okay, the other variable. All right, so now I have solved for y, and this y here is not a value, it's just an expression in terms of x. All right, and now we're ready for step number 4. All right, so now with step 4, once we have solved for y from this at this the end of step 3 right here, then step number 4 here, now I can write that a little bit in this space right here. Replace y, this y from the current at the end of step 3 right here, we're going to replace y right here by that symbol f inverse of x, because it is now, see, this is now a completely brand new function. Okay, so now we have our right to call this, hey, this is a function, this is y here is now a function of x, but now relative to the beginning function here, this is not the same function as f of x, but it's the inverse. That's why now I have my right to say f inverse of x. Okay, I replace that y symbol with x minus 3 over 2. All right, and ladies and gentlemen, we have found the f inverse, the inverse of our f of x function, or now I say f inverse, okay, of x. There are so many ways of saying that. So it's a demonstration problem. It demos the ideas of how we can get it done, and along the way it introduces. And this is the last step throughout all of our general guidance for how to find the inverse. Those major 4 steps are here. Once we apply those, it will guarantee that you land into the correct, the actual correct function, inverse function of a given function. But again, the work we are doing here is only valid, is only applicable after you have already decided whether your function will have an inverse or not. So it is extremely crucial that you check before you attempting this, find the f inverse. You gotta check if your function is a one-to-one function, okay, meaning it will have an inverse. So all we have to do is verify. All right. And so now, at this point, we are ready for a formal example. All right, so now let me introduce example number 2. Okay. So we want to find f inverse of the given f of x. Okay, we just want to find f inverse of the given f of x. So expectedly there will be part A, part B, part C, where each part is a different function, and we will be finding the f inverse. And so, like how I said earlier, yes, formally speaking, it is our responsibility to, on any of the given function I'm about to put here on the board, on any of those given functions, we need to first thing decide if the function will have an inverse or not. Otherwise, don't waste our attempt. But that is for you to work things out on your own practical situation. Right now, any of the problem I put on the board here is already decided, has already been verified that any of them will have an inverse. And so we can kind of skip that step. And so for academic purpose, for learning purpose, then any of the example with this wording just straightforward into find the f inverse, it's kind of assumed that the function has already been verified to have an inverse. So all you have to do is to take the next step, find that inverse. But for double the verification, you can always spend your own time double checking. Okay, so now this first function here, I'm giving out right here. All right, so how about f of x equals 2x plus 7. So like I said, this problem, this example, the entire example here has already intended that any of these functions given at you has already been verified that it will have an inverse. Okay, but it never hurt to double check. Okay, I can leave that double check for you to check. But now assuming that we already checked and we validated that it will have an inverse. And let's find that inverse. Okay, let's find that inverse. So here we go. That's our function at start. So first step, I am going to replace that f of x symbol here with the y variable. So y equals 2x plus 7. Allow me to write that a little bit small and break my board here into two separate columns with different space right there. Okay, so y equals 2x plus 7. That's really step 1 right there. And when you really are doing this and ready to turn your work in either to me or to your instructor, I don't think you even have to write these step 1, step 2. Just follow the steps and be clear with how the steps are connected. That will be enough to make your instructors satisfied, to give your instructor a satisfying view of your paper. Okay, and so now y equals 2x plus 7. So now the next step here is important step, interchange the x and y. Okay, interchange the x and y, meaning we switch row of the x and y variables in our equation. So now from step 1, the y variable from step 1 now becomes x. The x variable from step 1 now becomes y. So x equals 2y plus 7. That's what I meant by interchanging x and y. Okay, that's step 2. Okay, and now for step 3. From this point right here, we are going to solve, and this is where it's going to start taking some time. Okay, so step 3 right here, we want to solve. Okay, from this equation, we want to solve for y. And so allow me to bring in the solving steps here as well. Okay, so now x equals 2y plus 7, but you have seen a lot of arguments earlier, a lot of reasonings earlier when I was doing the demonstration. And in the end, this belongs to your prerequisite course, so allow me not to go too deeply into the details here. I'm going to subtract 7 from both sides. Okay, that brings my equation to x minus 7 equal 2y. And then I'm going to subtract, I'm going to divide both sides by 2. Okay, and now I'm ending up with, right, so x minus 7 over 2 to equal y. That's how I said I solve for y from this equation. X equals 2y plus 7. X equals 2y plus 7. I solve for y. Okay, so now I can allow me to switch over to the other board. So now I can rewrite my equation formally as y equals x minus 7 over 2. It's just me that I prefer to leave my solved variable on the left-hand side, the standalone, the single variable. I want to leave that on the left-hand side, and the other variable that's involved in an expression, okay, that's part of a whole expression, is on the right-hand side. It's just my style, even though you can always leave that in the other form, where it says x minus 7 over 2 equals y. This is also already a good point, a good finishing point of your problem already, solving for y. Okay? And now with your equation here to be successfully solved for y, now the last step here, we're done with step 3. So the last step now is simply just going to replace that symbol here, that y variable, by the f inverse symbol. So our f inverse, see, y now is a function of x. And this y here, of course, is different with the beginning function. This y here as a function of x is different with this f of x right here. So we are about to call this function x minus 7 all over 2 here the f inverse of x, okay? X minus 7 over 2. All right, and so now we have found it. I entirely skipped that step where we verify, where we were trying to decide whether it will have an inverse from the beginning, because it will. This example is intended that any of the given problem, any of the given functions will eventually have an inverse. So here we're going to find it. All right, so that's the end of part A right here. Let's look at part B. All right, so part B right here, let's look at the next problem of ours right here. How about f of x, okay, equals 4x cubed minus 1. 4x cubed minus 1. All right. And so again, this function was already verified that it will have an inverse. Okay, meaning this function we know for sure I mean we at this point we assume that somebody already tested for us, I mean verified for us and know and guaranteed that it's a one-to-one function, meaning it will have an inverse. And so in that way we just take on to the next step right here. But if anyone would like to have a double clarification, you can always hop onto a graphing utility and double confirm that this is a one-to-one function so that we can proceed. Okay, but now assuming that this will have a function, it's already been verified, then let's move on. So step 1 again, okay, I'm now getting into the steps of finding that inverse, that f inverse. So I'm going to replace that symbol by y variable. So y equals 4x cubed plus, and I mean minus 1. All right, so that's my step 1, and here I'm completely letting go of the steps. It's just, you've seen that often enough. So now just, replace that symbol by the y variable. That's the first thing. And then the next thing now I'm going to interchange. So interchanging the two variables means we're going to swap or we're going to switch their roles right here. Y becomes x, and x in the next step becomes y. So in the next equation, y here is x. So our equation reads x equals 4y cubed minus 1. That's what it means by interchanging the variables right here. Okay, so now the next step here, the third step, is to start getting into solving for y. We're going to start solving this equation here for y. Because right now, in the way how the equation reads, x is an expression in terms of y, but we want y as an expression in terms of x. That's why we need to solve for y. Okay, so now I'm going to take some more steps right here. So now x from this equation here, I'm going to add 1 from both sides according to the order of operation. So here that it's 4y cubed minus 1. So I'm going to add 1 from both sides. My equation here becomes x plus 1 equals 4y cubed. Okay, and then in my next step, well, allow me to rewrite that previous step here on the right hand side, on this right column right here. So now I'm going to divide both sides by that factor of 4. So this is 4 times y cubed. So I'm going to divide both sides by 4. Okay, that gives me x plus y, and I mean x plus 1 over 4 equals the 4 here on the right hand side cancel, so equals y cubed. But we are not finished. We are not done with our work solving for y yet, simply because right now it seems like we got rid of the coefficient, but we still have a power, a high power, and it's a one single power, one simple power, no coefficient 1 only, simply coefficient 1 and to a power. So the only way to solve for this, it's a cube power, so we take cube root. We take cube root on the right hand side and we take cube root on the left hand side. We take cube root on both sides of our equation. So in that way that produces now cube root or fifth root for anyone learning pre-calculus or learning at the college algebra level, you are the majority enough to know that cube root or fifth root, these are generally regarded as an odd root. Okay, so as a rule, generally anytime we take odd root, we don't have to do the plus and minus sign thingy. Okay, so now just simply y taking cube root of a cubic gives me just a y. Okay, and then here is a cube root of x plus 1 over 4. And what I meant earlier, unlike taking square root or fourth root, we don't need to have a plus and minus sign here. So now I have solved for, now allow me to swing on the other board right there. So now I have solved for y as an expression of x. That expression is cube root of x1, x plus 1 over 4. So x plus 1 over 4 is the entire expression being cube rooted. Okay, so you can see that the whole expression here, x plus 1 over 4, is inside my root. Okay, so I have solved for y. That's the end of step 3. So now step 4. And so clearly at this point, and apparently at this point, the right-hand side is only in terms of the x variable. There's only one expression right here, and it's y equals. So clearly speaking, this is y is a function of x at this point. Okay, and so now I can replace the symbol y here, this variable y, by the f inverse symbol. So now it's f inverse of x equals cube root of x plus 1 over 4. We have found another inverse function. This is the inverse function of our function from the beginning. F of x equals 4x cubed minus 1. Okay, that inverse function was this one right here, cube root of x plus 1 all over 4. Okay, so that's 2 problems down so far. 2 problems are being done. Let's try another one. All right, so so in part C right now, I still remember clearly in my example 1, I brought in the following function, and we checked with that function, and we already found that it will have an inverse. This following function, how about f of x equals cube root of x. That's why, like I said, the intention of this entire example is that any function given here is already known. Either we did that ourselves or somebody else already verified for us. Any of the functions given here is already known to have an inverse. Okay, so now this function from our example 1. Okay, see, we can make a note of that from example 1. We already knew from example 1 that it will have an inverse. So now let's find out what that inverse function is. Okay, so again, you gotta really nail this down, at least at our beginning level, to understand right here. This step right here is only to find that inverse, but it's only valid after you have already applied our understanding on one-to-one function, because to verify whether the function was a one-to-one, only one-to-one functions will have an inverse. Otherwise, it won't. Okay, and it's the truth like that. So at the end of the lecture here, I will have some time to explain the reason why, but right now we just get on the practical side. We're assuming that, we have already seen how we decided this function is one-to-one. Okay, let's find its inverse. That's all there is. That's why, like I said, from example 1, we already decided this function is one-to-one. It will have an inverse. So now I'm going to replace this symbol by the y variable, cube root of x. Now I'm going to interchange x and y. Okay, so in my next step, x becomes y becomes x. So here my equation in the next step reads x equals 3 cube root of y. Okay, so it's just a step that we break it down right there. And now I'm going to solve for y. Okay, so we have our y variable that we're solving for being inside the cube root, being inside the root. So the standard algebra work to get a variable out of a root is to raise that side to the power that cancel with this root right here. So here it's cube root. We need to raise the whole equation here, both sides, by the third power, because here it's cube root. So the only way to cancel cube root is we raise to the third power. So now I'm going to raise the right-hand side to the third power, and that means I'm doing the same for the left-hand side. It's another well-known rule to operate with an equation. You can always raise both sides of an equation to a power, to the same power. And now my equation becomes x cubed equals y. See, raising this expression to the third power, then now third power will cancel out with that cube root right there. That's why we're ending up with just that simple y variable. All right, so now we have solved for our y. We can write that as y equals x cubed to make it more friendly, to bring it into a more friendly form, like the form where we've been more familiar with. So now y is an expression in terms of x, or we can clearly see that now y is a function. This equation defines y as a function in terms of x. Okay, and so now the last step here to complete our work, we want to find the f inverse. So that y variable here, now I'm going to replace that with the symbol f inverse of x. Okay, and that equals x cubed. We are now done finding another inverse function. All right, so now the 3 problems in a row for this same example, we have found the inverse function. All right, let's look at another one. All right, so part D of our example. So now we're given f of x equals 5 over x plus 4. All right, so now once again, just another opportunity for us here to try. Okay, so this function is already verified by somebody else that it will have an inverse. So in our job here for this particular problem, we are going to take the next step, find the inverse of this function. Okay, without worrying about we need to identify whether it have an inverse or not, because somebody already let us know that it will have an inverse. But for guarantee, you can always spend your own time by pausing this video and do a double confirm on that, whether this function will have an inverse. Okay, but now I'm going to replace the symbol f of x by the y variable, and then we have 5 over x plus 4. Okay, and then in my next step, I am just like, so one general guidelines have been used for quite a few problems up to this point right here. It's about 5 problems we have done so far. Okay, and that shows enough generality of that guidelines I've shown earlier. So now in the next step, I am going to interchange, or I am going to switch x and y together. So y becomes x, and x becomes y. So my equation in the next step reads x equals 5 over y plus 4. 5 over y plus 4. All right. So now let's solve for y. So in the next step here, we solve for y from this equation right here. Okay, so according to the operation, then we have 5 divided by 4 plus, 5 divided by y plus 4. So according to the order of operation, then division comes before adding or subtracting. Okay, comes before addition or subtraction. And so in that way, to solve for a variable, then we have to get rid of the adding of the addition or subtraction before we get rid of adding, or before we get rid of division or multiplication. And so in that way, I am going to subtract 4 from both sides. We're undoing the operations. So now we have x minus 4 equals 5 over y. I did that because I subtract 4 from both sides, and that's consequently ended up with this equation. Okay, and so now in order to solve for y from here, I am going to multiply. I'm doing an algebra, a famous algebra step right here. I am going to do cross multiplication. This x minus 4 right here is really can be thought of as x over 4. X minus 4 all over 1. So now I'm gonna do a cross multiplication. Y multiply with that, and then 1 multiply with 5. So my next equation here. Now let's start anywhere starting from here. It's the steps that. So the steps can vary depending on the kind of equation you have, right there. Okay. But so now these are the steps how I solve for my equation in terms of how I solve for my equation for y in terms of x. So here by cross multiplication, I have y times x minus 4 equals 5, because y cross multiply with the entire x minus 4, and then 1 cross multiply with 5. I'm not saying my method of solving my sequence of the steps here is not the fastest sequence to get to the answer. You can have faster way of doing that, but I want to bring out all of the experience that anyone have seen in your previous course. Okay, so now at y times x minus 4 equals 5. Now to solve for y, to make y stand by itself, all I have to do now in the next step, divide both sides by that expression x minus 4. So x minus 4 is to be divided on both sides of our equation there. So our resulting equation now is y equals, see, x minus 4 cancel with x minus 4. Okay, this bar here is not a fraction bar, it's just kind of the way how it is, anytime we perform an operation, we draw a line through to draw the next step, to write down the resulting equation of the next step after that step was taken. Okay, and so now canceling out the x minus 4, my left hand side becomes y. Dividing both sides by x minus 4 gives me 5 over x minus 4 on the right hand side. So this is what my equation has become. So y equals 5 over x minus 4. The y variable already stands by itself on the left hand side. So we're quite very close actually to the final answer here. So all we have to do at the last step, replace this y variable by the f inverse symbol. So now our function here, f inverse of x is going to be 5 over x minus 4. That's how I have found the inverse for this function. Okay, so f of x is 5 over x plus 4. See, these two are different functions, different rules. Different rules about what to do with their own inputs. But now, if these two functions, these two different rules, they have a connection with each other. They have one connection from each other. Okay, and we call them, they are the inverse of each other. Okay, so this function is the inverse of f, and f is also the inverse of f inverse. All right, so those two. So now we found the inverse of f of x. All right, so now let me now give in an FYT right there for anyone to try to work independently on your own. All right, so now as an FYT, let's find the f inverse of, how about f of x equals, and here we're looking at 8x cubed plus 1. All right, 8x cubed plus 1. All right. So now here's the answer. Tentatively, all right, so now go ahead and pause the video. Okay, go ahead and pause the video and get the problem done. Find your own f inverse. And once you resume, I will only show the final f inverse without showing the steps anymore. Okay? All right, so now assuming you have already had spent some time, the f inverse for this function, these are your steps right here, whatever that will be. F inverse here will arrive at cube roots of x minus 1 all over 8. Okay, that's a successful one. Now, algebraically, for this particular one, we can step one step further by taking advantage of the root property. We can break that down as it's a cube root of x minus 1 over cube root of 8. And so now I realize cube root of 8 is actually a 2, because 8 is a perfect cube. And so now this is the same as a 1/2 cube root of x minus 1. These two are equivalent, or exactly the same expression. It's just in different form right there of expressing it. All right.